inverse trigonometric functions. So we've seen our trigonometric functions and we've graphed them. This is y equals sine of x, and we have a curve, and that curve goes on forever in both directions. I just plotted a couple of points at pi over 2. Sine of pi over 2 is 1, so we have the point pi over 2 comma 1. If we look in the negative direction, we have negative pi over 2 comma negative 1. And so those are just 2 points on my graph. If we take the inverse, which means we switch the x and the y, and we solve for y, so x equals sine y, take the inverse sine of both sides, and we have sine to the negative 1 of x is equal to y. Well, when we do this, when we're switching our x and y's, our values don't form a function. So if we were to take a vertical line and draw a line down here, for an x value, we're going to have infinitely many y values as we continue down here. So the inverse in this case is not a function. So what mathematicians did is they played with the curve y equals sine x and just took a section of it. So, and they call this y equals capital S sine x. So that capital S just means we're taking a section of it instead of the whole curve. And we take it from negative pi over 2 to pi over 2. So just this section right here. Now when we take the inverse, x equals capital S sine y, and solve for it, that's why oftentimes you'll see our inverse sine capitalized. So that inverse sine of x is equal to y, and that just looks like this, which is a function, because when we have our vertical line, our x only yields one y value. Now notice right here, if we have that negative pi over 2 comma negative 1, we switch the x and the y's, and we have negative 1 comma negative pi over 2. So here my values are negative 1 and 1, just because they were 1 and negative 1 over here, and now those are my y values. And my x values right here were pi, or right here, negative pi over 2 to pi over 2. Those are going to be my y values, negative pi over 2 to pi over 2. So taking just this section, we can have an inverse trigonometric function. We can have sine to the negative 1 of x, capital S, equal to y be a function. So the other trigonometric functions work as well, and these are just 3 out of the 6. You can do this with all 6 of them, just taking that section. So y equals sine of x, that's just a section of sine of x, and then the inverse would be y equals arc sine, or sine to the negative 1 of x, or inverse sine, and that looks like this. Y equals cosine. Now notice that's a capital cosine. So the cosine curve we know goes like this, and that goes from 0 to pi. That's the section. So it's a different section. We take the section from capital sine of x, from negative pi over 2 to pi over 2. From cosine of x, we're taking from 0 to pi. And that way we can get both of our positive and our negative values. Because in cosine of x, if we think of the unit circle, cosine starts positive and then goes negative. And sine, if we took that same interval, would be positive the whole time. So we're taking the section from 0 to pi, and it includes both of those. That's what that closed bracket means. And the inverse would be y equals inverse cosine of x, and capital C here. So same thing with tangent, and tangent we're going to take with the same values we took sine with. So negative pi over 2 to pi over 2. And tangent, remember it's periodic and it's going to continue. It doesn't continue like cosine is not continuous, but we have sections over here. So we're just going to take one of those sections between the asymptotes. And so then y equals inverse tangent. The x's become the y's, and we have it look like this. Notice it's a function, and it does have 2 horizontal asymptotes because it had 2 vertical asymptotes in the trigonometric function capital tangent of x. So the inverse tangent of x would have those same ones, only they would be horizontal asymptotes. And so that's kind of what the visual of what we're doing when we're taking these sections of the sine and cosine and tangent curve. And you could do the same with the cosecant, secant, and cotangent curve. So looking at these inverse functions, write the equation in equivalent inverse form. And we've already done this a little bit when we're solving. So sine of theta equals 1/2. That means what angle or what arc is going to give me 1/2 for my sine value? Well, if this is on the unit circle, it's pretty easy to answer, but we're only just rewriting this in inverse form, so the equivalent inverse form. So taking the inverse of both sides, I have theta is equal to sine to the -1 of 1/2, or inverse sine. The other way you can write that is theta is equal to arc sine of 1/2, and that arc sine comes from what arc is going to give you 1/2. So how many radians do you arc over to give you 1/2, or degrees? So tangent of y equals -3, just rewriting in inverse form, it says the same thing as this says, it's just in a different form, and it's solved for y, or for that theta. So y is equal to inverse tan, and it's capital T, of -3. So we could also write y equals arctan of -3. So that's just rewriting in the equivalent inverse form. Now we can use that to actually solve some of our equations. So say we have x is equal to inverse cosine of rad 2 over 2. We can also say arc sine of rad 2 over 2, and it's asking the arc where the cosine is equal to rad 2 over 2. If I recognize this as on my unit circle, I can use my unit circle to figure out the degrees or the radians of the angle and that arc, that corresponding arc that go along with it. Cosine, remember, is defined, big cosine with the capital C, is defined from 0 to pi. So I'm only looking in these first two quadrants. And as I go around my unit circle, I recognize the rad 2 over 2. And in a unit circle, it represents my x value, so right here. And I know that that's going to give me pi over 4 is the angle or the arc that gives cosine rad 2 over 2. So x is equal to pi over 4 in radians, or 45 degrees in degrees. Number 2, arctangent of rad 3 equals x. Now, tangent's a little bit tricky because you're dividing two numbers in order to get that. You're dividing your y over your x value in our unit circle, actually in any trigonometric equation. So this rad 3 is a little bit hard to recognize, but as you do more problems, you'll recognize it more and more. So you want to look for, when you divide your y divided by x, you're getting rad 3. And so you obviously have to have a rad 3 in there somewhere, and you recognize that is the only thing you have is rad 3 over 2. And arctangent, remember, is only between negative pi over 2 to positive pi over 2. So it's these two quadrants. And I know this is positive right here. And so I know it's not going to be this fourth quadrant. It's got to be this first quadrant. So I have two possibilities where I have that rad 3. The first one I checked is pi over 3. And I know I'm having my y over my x. And so rad 3 over 2 over 1/2. And I'm going to see if that gets me rad 3. So rad 3 over 2 divided by 1/2, that's the same as rad 3 over 2 times the reciprocal of this one, because this is just a division problem. The 2's make a 1, and I have rad 3. So at pi over 3, or 60 degrees, the arctangent of rad 3, that's the arc length that's going to give you rad 3 for the tangent. So you want the arc where tangent equals rad 3. And you can write it in degrees or radians. You'll have to see what's asked for in the problem. So finding each values, we're just kind of building them. They're like composites. So we're taking the cosine of the arc sine of this angle. So here, when you're taking the arc cosine or the arc sine, you're trying to come up with an angle that gives you this value with the trigonometric function. So this is going to give us an angle value. And then you're going to take a cosine of that angle value. You always do the inside first, kind of like order of operations, but you're always doing what's in the parentheses first. So the first thing I want is inverse sine of rad 3 over 2. That is, what angle or what arc is going to give us rad 3 over 2. So that is something that's on the unit circle. I can look at the unit circle. I'm going from negative pi over 2 to pi over 2, so that's where I want to look, because there are two places where this is true, but we're only looking in this section right here from negative pi over 2 to pi over 2. So when I look at that, I find that that's going to be my 60 degrees, or pi over 3, just looking at your unit circle. And then I want to find the cosine of 60 degrees. Again, I can look at my unit circle, and I find that that's 1/2. So that's my x value at 60 degrees on my unit circle. So number 2, the tangent of the inverse tangent of -1. So remember, my tangent is defined, my capital tangent is defined from -pi/2 to pi/2, and I know it's going to be in the 4th quadrant, so it's got to equal that -1 because it's a negative number. So looking at my unit circle, I'm looking for a y and an x value that match, because tangent is y over x, and if they're matching values, I'm going to get a 1, and I want a -1. So the only place that's going to happen is in that 4th quadrant, and I know it's got to be between these two values. So -pi/4 is going to give me that -1. So looking at the unit circle, going down to pi/4, I have my x value as rad2/2, and my y value as -rad2/2. So dividing those two, I get a 1. And then I want to find the tangent of -pi/4. Well, that's just really undoing whatever I did here. I want the tangent of that angle, which I know is going to be -1. So because these are inverses of each other, they're going to undo each other, and I'm going to get right back to that -1. This one is a little more complicated. I have 2 times the cosecant of the cotangent of rad 3. So first I want to do this inside section, and I have cotangent of rad 3. So I want to think about the unit circle, and I want to think, where is the cotangent equal to rad 3? Cotangent is x over y, so I want to look for the top value over that bottom value, and the top value will be x. So here I have an x value that has rad3/2, and if I divide it by 1/2, which is my y value, I have rad3/2 over 1/2. That gives me rad 3, and that happens right here at 30 degrees. So it's also pi/6, so I could have pi/6 there as well. So then I have 2 times the cosecant of 30 degrees. And instead of thinking of cosecant as 1 over y, I just rewrite it as 1 over sine, because I can remember that a lot better. And then I have 2 times 1 over the sine of 30 degrees. So the sine of 30 degrees, I can again look at my unit circle. The sine of 30 degrees is my y value, which is just 1/2. So I have 1 over 1/2 times 2. That's 1 divided by 1/2, or 1 times 2 over 1, which is just 1 times 2. And that gives me 4. So this just means I'm going to multiply by 2 at the end. All right, so let's look at one that's not on the unit circle. So we have the sine of the inverse cosine of 4/5. I don't recognize 4/5 on my unit circle, so I can't find it and find that angle measure that way. So I'm going to need to use my right triangle. Let's go ahead and make sure this is right. My right triangle and my trigonometric ratios. So since 4/5 isn't on there, I'm going to draw my right triangle. I have an angle theta. I know I want the cosine to be 4/5. Cosine is the adjacent to the angle over the hypotenuse. So 4 is my adjacent over the hypotenuse, which is 5. And so then I want to find, so this is my angle I'm talking about. So cosine, arc cosine of 4/5 is going to give me this theta. Now I don't actually need to know the exact measurement of that angle right now, because I'm going to take the sine of whatever angle that is. So this angle that makes the cosine look like this, I'm going to take the sine of it. So sine of that angle that makes this true. Sine of that angle is opposite over hypotenuse. So here's my angle, opposite, which I don't know, over my hypotenuse, which I know is 5, from this right here. And so I need to find my other side, and I recognize that right away as a 3, 4, 5 triangle, but if you don't, you can just solve for it. A squared, which is 4 squared, plus b squared, is equal to c squared, and then solving for b, and I get 3. So I have a 3, 4, 5 triangle, and now I can take the sine of theta, which is really what I want, that sine of that angle that makes this true. And so sine of theta is the opposite, 3, over the hypotenuse, which is 5. So sine of the inverse cosine of 4/5 is 3/5.